Okay, so I have some good news for everyone today. I'm not going to be talking about chemistry. Okay? You've probably had an entire week of chemistry now and you're probably sick of it. So, the original plan was for Tom Quinn to talk about quite a lot of quite a lot of the SPH details last week. And then this week I would then focus more on the chemistry, and that's kind of how we try to work it. I think last week he was talking quite a bit about the how to parallelize tree codes, and he introduced SPH a little bit, but I don't think he really got the time. He felt like he didn't get the time to cover the SPH fully. So I was going to introduce a few more things today, and I'm going to call them SPH extras here because that was the original title of the talk that I submitted to Mark. But I think in some cases these are in some ways more SPH fundamentals, and there are things which people have mentioned them in passing over the week, and then we've kind of skipped over them. I just wanted to focus on them a little bit more. So this will be more like a kind of a how-to of SPH. If you have any questions, then please stop me and ask me, and I can show you the movies again if you're interested and you didn't see anything the first time round. Okay, so please be as interactive as you can. So So first of all, I should say before I start, there are some nice reviews of SPH. Those of you who use SPH have probably encountered them already. There's a very nice one by Stefan Rosvog, which was done in New Astronomy, and it has some nice images in there. It's a good introduction to SPH, and also if you want to do special relativistic SPH, he also introduces the equations there as well, okay? Because that's what his work uses that. So he's been key in developing those equations over the years. Dan Price is the other SPH guru. He spent many years with it. Those of you who have seen his talks, trying to put MHD into SPH, and I think he's had some success recently. He's had a lot of failed attempts over the years, and those failed attempts have been very interesting because they've shown parts of the SPH algorithm that we don't understand, and ways in which it can be improved. So he's actually gained a huge amount of insight into doing normal SPH, standard hydrodynamical SPH, by trying to do the more difficult problem of the MHD. And he has a really nice review in the Journal of Computational Physics, which was I think it's subtitled "Things I Wish My Mother Taught Me" or something, and to do with SPH. So please go and have a look at his paper. And much of little plots that I'm taking today, and I'm showing you in the movies I'll be showing you, many of them are from Dan. I got some. He sent me some movies via email last night. There's also been a couple of papers recently which have updated the SPH algorithm, and I think it's kind of good to have a look over them. One particular one, which I think Dan Price would also say is probably the state of the art for how to do shock capturing and stabilizing the SPH solution, is this paper by Cullen and Denon. It's quite a complicated method that they've introduced here, and it does introduce an extra overhead in doing the SPH hydro. However, if you're doing gravity anyway, you probably don't really see that in your code. Okay, so it's probably worthwhile implementing their switch. Justin Reed and Tristan Hayfield have also done something very similar. They've kind of extended what Cullen and Denon were doing to, instead of just using it for capturing shocks, they're using it for capturing all discontinuities in the SPH equations. Okay, so they've kind of extended that, and they've got a nice paper on that too. And then Phil Hopkins has this paper where he kind of derives more general types of the SPH equations, some of which may be more useful depending on which problem you're trying to solve. Okay. So so I was talking to Phil yesterday. He was saying that his go-to method that he's using is a combination of the outline that he's got in this paper with the Cullen and Denon viscosity. Okay, so that you could say would be the state of the art at the moment. Okay. So the first thing I'm going to talk about is number of neighbors. When grid code people get together, they all talk about what reconstruction technique they use or which Riemann solver they're using, right? When SPH people get together, they tend to talk about the number of neighbors that they're using in the calculation. And people come up to me in conferences and say, so how many neighbors are you using? And I say, well, I always answer, I'm using the cubic spline. There's a long silence, and then we kind of both start looking at our shoes, and it's very awkward, and then we generally shuffle apart from each other and go and talk to someone else. So what's going on there? So I should probably point out that the number of neighbors that you have is not an option, okay? It is fixed by the type of kernel that you have. And so where does this come from? Well, the idea is that SPH is trying to approximate an integral form interpolation theory by doing a sum over the neighbors inside a certain volume, okay? And that volume is set by the smoothing length, and you try and have it such that the smoothing length contains a fixed number of neighbors of some description, okay? And as you get into denser regions, that smoothing length gets smaller because you're looking inside a smaller zone. And in the more recent SPH iterations, the smoothing length and density are actually fixed very visually to each other. You can almost throw away one of those now. You only need one or the other. They're essentially equivalent to each other. And so the H sets the number of, if using compact support kernel, the H sets the volume inside which you look. Okay, so there's a fixed number of neighbors inside there, and you would think that by increasing the number of neighbors, so say your particle is the red particle here, and you say, okay, I want to get the SPH properties at that particle, so I'm going to look over some volume, I'm going to pick out the neighbors inside there, and I'm going to do the averaging process to get my quantities. And you think that because you're trying to approximate an integral with a sum, that just by having more neighbors inside there, you would then get a better estimate of that sum. In fact, what you're doing is you're reducing the truncation error. You're not actually getting a better estimate of the SPH properties. And the reason why can be summarized in that movie. Okay, do you see what happened there? I'm going to start it again. So the problem is this. I should maybe I go back to the. Okay, so what happens is that was a. Oh, sorry, the movie is playing by itself. I wanted not to do that. Very quickly, I'll just go over here, fix it. Okay, so what we have to start with are SPH particles in a box. There are no velocities there, and they're on a close-packed mesh. Okay, so that means rather than having particles here and here in a kind of regular grid, they are put such that a particle here, and then there's the next particle, the nearest one is on the diagonal. Okay, so they're kind of pushed together. And you think that's a very stable arrangement. It turns out SPH doesn't like being in that arrangement and wants to be in a different rearrangement. And what happens is, when you're doing the smoothing over your, when you're doing the SPH summation, you're making some errors. Okay, so SPH works by a particle hitting another particle. Okay, unless there's another particle on the other side which exactly mirrors that hit, there's going to be some movement, and the particle in question is going to then move off slightly in a different direction. And so what happens is, for a while, this arrangement is stable, and then one particle says, no, I don't like it. And it just moves a slight little amount, and then everything else has to move. The entire grid then just changes. Okay. And the second thing you'll see is then that the particles start to pair up when that happens, and they move towards each other. Okay, so the number of neighbors here was, so it's the cubic spline, the standard spline that everyone is using, and it's using 100 neighbors. Okay, so you think 100 is better than 50, I'll get a better estimate of what's going on. And if you watch what happens, it sits and wibbles for a while, then they all move, and then they kind of flip together, and then they pair up, and they create this kind of lattice arrangement. Okay. Now, this arrangement, this complicated lattice arrangement, which you see the particles go into, is what SPH wants to be in. It wants to be in this kind of, it wants to minimize the energy in the lattice. Okay, so it tries to do that live in the simulation. And so what happens is you start off with a close-packed lattice with n equals 100. The particles start to pair up. You can see it happening here. And these guys have sat on top of each other now. And then they end up in this kind of more sparse configuration, which has this kind of nice kind of hexagonal shape. And you end up with about half the resolution that you wanted, because the two particles are sitting on top of each other. They're not really sampling all the points in that volume very well. Okay, you now get two particles essentially giving you the same estimate of the fluid instead of having a slightly different estimate of the fluid, right? You've lost kind of that, not resolution I want to say, but you're not sampling the volume as well as you were before. So what's happening? So here's the kernel that you're using. This is the cubic spline kernel, and the line on the black at the top here is the shape of the kernel given in terms of the smoothing length, and the cubic spline goes out to 2h. Okay, so you set h by trying to iterate over density in your neighbors to get some fixed number, and then you use this kernel inside that for whatever h you've got. Okay. The red line here at the bottom is the gradient of that kernel. Now you see it's always negative, but it is essentially the kernel is flat in the center, so it goes to 0, and then again the kernel goes flat. It's a spline which goes flat, which goes to 0 at around about 2h. Okay, so what's happening? So if you imagine particles pairing up, they're going to hit each other and they're going to move around. They're going to move around inside the kernel. The problem is that when they go under this hump in the kernel here, they don't experience quite a good a force in trying to push each other apart as they did when they were over here. The momentum equation has the grad of the kernel in it. Okay, so this is how the SPH is actually doing its interactions with each other. And so if you have a particle which was, say you've got 3 particles in a line and one of them is slightly closer to the other one. Okay, so what happens is that it feels a big push from the guy which is further away because it's getting it's in a better part of the kernel, say over here, whereas if it's closer to the other particle, then it doesn't feel such a big push and it gets slipped towards. It slips towards it. Okay, so the particles go under the hump. Okay, so they all start to pair up under this point here. So the optimal configuration and the number of neighbors you have is such that your nearest neighbor is round about here in this kernel. Okay, if it slips below that, the particles will start to pair, and then you lose that spatial sampling of the kernel. Okay. Now it turns out for the cubic spline, the optimal number of neighbors is 57. If you use any more, they'll pair up and they'll be useless. If you use less, you're going to then get some truncation error, right? So the cubic spline can only use 37 in general. And so if you want to use more neighbors, you have to go to a higher order kernel. Okay? You can't stick with the same one. And so the cubic spline goes to 2H, 57 neighbors. You then have these other kernels. I can't actually remember the exact number of neighbors. I think this is like, well, I think the quintic kernel goes up to like, it's over 100, 150 neighbors or so. And the quintic kernel goes up to 3H, okay, so it goes all the way out to 3H. And people were always saying, well, I don't want to go to 3H because then I lose resolution in my simulation, right? And then I'm, H is my resolution element. No, that is wrong. H is still your resolution. That's the same as your grid cell in the fluid code, okay, in a normal grid code. Your resolution is still dependent on the smoothing length H. It doesn't matter that you're going to 3H. And the way you can think about it is if you have a Gaussian kernel, the spread of that kernel is still H in terms is going to be the standard. It's going to be the dispersion of the kernel. But the Gaussian has no compact support. It goes to infinity. And technically, you have to involve every single particle in the simulation. But we know still that in a Gaussian kernel, you still have H as being the resolution element. So that's the way to think about it. Okay. So if you want to use more particles and get a better estimate of the errors that you're making inside the smooth length, you have to use a different kernel. You cannot just simply increase the number of particles under your kernel. Now you will find that people will say, well, when I used the more particles under my kernel, I did actually get better results in a sense. Pardon me. And that is because it takes a while for that clumping and that pairing to occur. So if you're constantly moving the particles around, it may get broken up and it may not happen every so often, and then so you are beginning to sample the volume inside the kernel. Okay. So yes, in some case, if you're using a very dynamic situation, then just by increasing the number of neighbors will give you a slightly better estimate for this particular kernel, but it's not guaranteed for all cases, especially when the gas becomes more relaxed and the velocity starts to slow down. Okay, it becomes more of a steady state. Right. Okay, so that's any questions on that? No. You knew that already. Good. Okay, so here's a kind of movie. Just goes. I think is it going to repeat? Oh, maybe not. Sorry, my movie's wrong. Going horribly wrong. Schoolboy error. Repeat. Okay. So this is what happens when you spray particles initially at random into the simulation. You start with random configuration, and over time, over like maybe a couple of crossing times or sound crossing times, the particles will then rearrange themselves onto that lattice. Okay. So just to kind of idea, the SPH, even if you did start with something totally random, and some of you might be starting with your initial conditions fairly random, you'll notice that if you look a little bit later in the simulation, that you have regularized your mesh. Now, obviously, there's lots of movement of particles in here, which is kind of unphysical in a sense, right? You don't want that in your solution. So you have to be careful. The SPH always has this low-level amount of noise in the velocity, which is just the SPH particles trying to reorder its mesh. It's not really the main fluid bulk velocities. Okay, so you always have to be careful there. But it does mean that the particles won't get themselves into a real mess and a real pickle. They will try and wash it out. And we'll see situations of this later on, okay, when I come to talk about shocks. Okay, so bringing stuff on to shocks. So there's always this other things. People are saying, well, can SPH capture shocks? And everyone says SPH does a bad job of capturing shocks. That's what you always hear, right? Okay, so SPH actually does quite a good job of capturing shocks. It just smears it over several H. And the reason why it's doing that is because it's using artificial viscosity. And as Jim was saying, I think yesterday, he was talking about this, the artificial viscosity terms will tend to smooth your shock over several grid cells. And the reason why is that you've taken normal viscosity which is trying to act over a very, very small layer in a fluid, and you've bumped it, because you're not resolving that tiny layer, you're actually resolving huge layers coming together. You have to bump it up by orders of magnitude, huge orders of magnitude, to make it be able to capture those big, big flows that are coming together. Okay, so that's why it's called artificial viscosity. And what it does is that it tries to smooth out the contact discontinuity between the two states in the fluid, such that either grid codes can be stable over that boundary, or in the case of SPH, it'll also be stable, but it can also then resolve it, and it can see what's happening, okay? So we'll come on to this later again. We're talking about Kelvin-Helmholtz. There are situations where SPHs can't see what's actually meant to be there, because it's a form which is alien to its interpolation properties, okay? And so you find out when you put so standard SPH artificial viscosity, this is the standard alpha and beta viscosity that was used here in Stefan's review paper in 2009. He was doing the solid shock tube, and you see in one dimension SPH looks pretty good. Okay. Yes, if you zoom in, you'll see that SPH is overshooting, undershooting sometimes, but it's getting all the properties correct at the various different points. It's just spreading out a little bit further in terms of H, the solution. Jim.
Since you brought this up, I mean, the key here is that it's one-dimensional.
Yes.
So the particles can't interpenetrate. If you do the same test in 3D, you'll get a very different answer.
Yes, that's my next slide.
Okay.
Okay, so yeah, SPH looks just fantastic. And the reason why is that the particles, I mean, as Jim's saying, they've got nowhere to go but left or right, okay? And then they hit something else going the opposite direction. And because you've smoothed out the discontinuity, SPH can see what's happening, and then because SPH is conserving mass, momentum, and energy in these formalisms, then it will capture the shock. It will do the right thing. Okay. Okay, but if the details of your shock front are important, for example, if you were doing very detailed shock chemistry, then obviously SPH is an extremely poor choice, because it's then changing the properties of the shock over the shock front. Okay, so then if you want to do so I'm meant to be talking about chemistry this week. If you want to be doing shock chemistry, don't do it in SPH. Okay. So, as Jim's pointing out, in higher dimensions, what happens? So here's the same, well, here's a different type of shock tube, solid shock tube, but it's basically the same idea. And this is it done in 2 dimensions with the cubic spline kernel. Okay. Now you'll see that in general the properties are still pretty good. If you look at things like pressure, it doesn't look too bad. There's a small blip. The wall heating term you get, that is just from the fact that SPH can't quite smooth out the discontinuity fast enough, and so it does see a bit of a pressure blip. The density doesn't look too bad. Again, the internal energy is going to be kind of the same. There's a small overshoot here, which is what's causing this here. That's not quite right, sorry, the overshoot's here. So yeah, it does overshoot the energy slightly here. But you notice, as Jim's pointing out, you get this horrible mess in the velocities. So what's going on there? Well, the problem is now you've given the SPH particles an extra dimension to play with. And so instead of just being able to go backwards and forwards, they can now go to the side. And if any errors you make when the two flows are coming together in your interpolation, if the forces from the neighbor sum aren't exactly balanced, the particle will move to the side slightly, okay? And then you're introducing an extra source of error. And so you're creating noise in the mesh, which is just from the SPH noise, okay? And so you're removing some of the energy in your simulation, which should be going straight into the shock, and you're putting it into transverse modes, okay? So then the SPH starts to do a worse job.
Is this every particle being plotted here, or is this averaging together?
That is every particle, I think.
It seems to be not very many particles, because there's only like 5 particles in the shock out of the whole 3D mesh.
Yep. 2D, that's in 2 dimensions.
But it's a 2-dimensional shock front, so there must be more than 5 particles. I think this must be binned.
By, okay, it's not, Dan doesn't say actually in this thing, yeah.
I have a plot from Gadget. I can show you later.
Okay. Yeah, you're right, it could be actually, yeah, you're right. There's not very many there in the shock. That's true, there'll be many, many more. Okay, yeah, it could be. So what's kind of happening, you can see how this happens if we look at the particles, if you actually plot the particle positions in the shock, and maybe, I hope you can see this clearly enough. There's a problem with particle plots, it's difficult to see in a big auditorium. So here's the initial conditions for a shock. You have kind of denser side on one side, you get a low density environment, and then you've got different amounts of energy over the two. And here's what happens sometimes later. You'll see that this stuff is pushed into here, obviously. The shock front's now over here somewhere. And what you find is that over here the particles are quite regular, close to the shock front, it becomes a real mess. Okay, here's your mesh beginning to have errors in it, and the particles trying to figure out what they're doing when they see all these truncation errors and kind of summation errors from doing the SPH summation. And then downwind again, then you see is still quite regular. Okay, so it takes a while for the SPH particles to shuffle themselves around, and all that shuffling is obviously reducing energy from the system, and so it is then creating not such a good shock as you're getting in the 1D case. Okay, and obviously this gets worse as you go to 3 dimensions, because you then introduce a second lateral component to the shock, which the particles can then move in. Okay. So how can you fix it? Well, you can't really fix it entirely. It's always going to be there, right? The SPH has to restructure its mesh at some point. But what you can do is try and beat some of the error down, again, by using a higher order kernel. And this is the same shock as before. So basically it's this one here. This time using, instead of the quintic kernel, which has the 57 neighbors or so, it's now using over 100 neighbors in the quintic kernel, and you find you get a much better estimate of the shock. Okay, so you see still some remeshing errors there, but it is damped down. Okay, so the reason why is that now SPH can actually grab a much larger. It's now trying to stabilize its local velocity in the transverse component to the shock by looking over a much larger distribution of particles, and there's more chance that those summations that it's making from both sides will start to cancel out and stop that kind of particle wobbling around. Okay. So again, if you use a higher order kernel, you do get better results in general. The second rule of viscosity, so that's one rule of viscosity, is that it captures the shock. It actually allows you to capture things and remove those contact discontinuities. The second rule is that it also helps minimize the amount of wibbling of a particle at any one point. Basically, the particle, if you imagine SPH is a wee bit like having a bunch of protons in a bag, right? They don't like each other, they're constantly trying to move away, and they're constantly trying to find the minimum energy state. If you were to put the protons in a bag instead of a bag, put them in treacle, then obviously they won't move around as fast, right? You won't have all that constant velocities moving around. You are draining energy from the system, so you have to be careful. But so the other role of viscosity in SPH is to stabilize the particle distribution. And here's a bunch of particles that have been put into a box. They've just been put in totally randomly. And then you let them settle, and you find that without the artificial viscosity, it takes a while, but they eventually do get to having some sort of the glass-like structure that they want to have. But it happens much quicker when you include the viscosity, right? Already at half that time, the viscosity has allowed the particle distribution to settle, and then it creates that kind of nice mesh. Okay, so that's the other thing why it's kind of almost sometimes dangerous to have zero viscosity in SPH, because you want some of it there to help regularize the particle structure. Okay, so that's why people tend to not use zero viscosity entirely when they're doing these decaying viscosity formalisms. Okay, so we mentioned that basically the artificial viscosity is a kludged up version of molecular viscosity that allows you to solve the problem at the scales at which you've now put it in the code. If you have very, very strong shocks, as Jim was talking about, instead of just having this the particles moving transversely to the shock front, if they don't get checked entirely, they can just slip straight through each other. Okay, particle interpenetration. The two streams slide past each other, and that creates a huge mess. Right? You've then removed your shock front, and essentially you've kind of smeared it out in space even further, and also you're just introducing huge amounts of error. Okay, so you're not removing the energy from the shock that you should have done, and the particles stream through each other. You've also got this extra amount of velocity there, which is also wrong. Okay, so you've not removed the energy from the system properly. And what Dan Price and Christoph Federat were doing in the paper in 2009, they were comparing a grid code. I think in this case it was using, I think it was fixed unigrid flash, I think it was. And Dan was using his very lightweight SPH code, which is called Phantom, which is an MPI code, which he's trying to get such that it's incredibly, incredibly fast and has a very small memory footprint. So he's done a lot of kind of tricks there, that, taking out things which are normally in an SPH code to help it run help it run, but use up memory. And he's tried to do it in a kind of much more fast and clever way. And he was then doing a comparison with Christoph and looking at turbulence. And what he found was that if you use the same number of particles as you have in the grid codes, then yes, the properties of the turbulence actually look pretty good. The problem is the SPH calculation is much more expensive, even in his stripped down code, right? Because you have an unstructured mesh, you have to go and find your particles, you don't know where they are, right? So that's always going to be an issue. But what he was finding also was that the ability of it to capture the shocks and to get nice kind of clean shocks and stop that penetration depends on what he was choosing for the beta viscosity, which is the one that's a non-linear term, kind of like the von Neumann-Richtmeier viscosity, that allows you to, that stops the particle in the penetration. And so he was saying the standard value that people use is either 1 or 2. And he was finding it was actually quite noisy. And then when he ramped up to around about 4, he was getting much, much sharper shocks, and they were beginning to look better. There was less particle in the penetration, and that was that also affects your power spectrum of turbulence, because you might see that those velocities streaming through each other, and you might, if you were not being careful, you might then put that into your power spectrum analysis and then say it's some sort of small scale velocities, okay, which is wrong. So you want to have lots and lots of AV in the artificial viscosity in the shocks, but you don't want to have very, very much at all in the low density environment. Remember, in places where they're not shocks or where the particles are not disordered, okay? So the question is, how do you get rid of it? Otherwise, if it's always there, it's always just going to drain energy from the system. You want to get rid of it entirely at some point, or get it very, very small. A fix that Morris and Monahan came up with in 1997 was to have this idea of a time-varying viscosity. The idea is that as you approach a shock, the viscosity ramps up to some kind of maximum predetermined value, and then as you move away from the shock, the viscosity tries to damp down. It tries to damp down within a few smoothing lengths of the shock front. Okay, so it's just gone by that point. So it's enough there just to help it regularize its particle mesh behind, and then it's gone. Okay, so you're back to more of an inviscid flow, and then if you have shear, for example, you shouldn't see the shock draining out some of the energy in the shear. And they did it the following way. They said that the alpha viscosity here, so the beta is in their prescription was just some function of alpha, so say 2 times alpha or whatever, and some minimum term. Then you're trying to kind of let it decay. There's a decay term, so the I is for the particle, there's a decay term for that particle, and there's a source term. And the source term is what ramps it up close to the shock, and this decay term gets rid of it away from the shock until it goes back down to some minimal value. And the source term is then, they've decided it's based on the negative of the velocity divergence, the idea being if you see 2 flows coming together, you need to ramp your viscosity up so that it can capture that shock. Okay. And that seems to have improved things dramatically, especially if you're looking at protostellar disks. It means you can reduce the viscosity in the disk. Generally, you don't have much shear viscosity there, because then this, the standard alpha, which is producing the shear viscosity, then drops down to some smaller value, and then you hope that gravitational torques are providing a bigger effective viscosity at that point. But then if you do have, say, a spiral arm shock, then the viscosity can ramp up, deal with the spiral arm shock, and then ramp back down again afterwards. Okay. Now, there are still some issues with this. It all depends just quite how you pick these source terms and also the decay term. And what Cullen and Denon found was that the source term doesn't always act fast enough, and it can actually lag behind, especially in very, very oblique shocks. It can get confused. And one of the reasons why is that the velocity divergence in SPH is quite difficult to estimate, partly because it has all that subscale noise, right? You're trying to estimate it by smoothing over your kernel, and you've already got noise in there, so that estimate is already going to be noisy to start with, and then you're trying to look over a very small regime to estimate the shock which is about to come. So what they did instead was they kind of did 2 things. First of all, they did a much more accurate estimate of this, which I won't go into, partly because I don't understand exactly how they've done it. Most people I speak to don't either. So they got a better estimate of how to the velocity divergence, and then at the same time they also used the time, the rate of change in the velocity dependence, the velocity divergence, to ramp the shock up. So they got a kind of a much kind of quicker source term there, okay? And then they use a slightly different term for the decay term as well. And they found that when they were doing a standard test here, you just put a sound wave through the box. Standard SPH is really bad. After like 10 periods, it's already creamed most of the energy out of the system, and the sound wave is essentially gone. Fokker-Springel, so in the paper by Bauer and Springel, made a big point of this in the recent paper. It had already been shown in Cullen and Denon. Something's been shown for a long time. Okay, that SPH has a problem when you get into the subsonic regime, just because of the viscosity and also the noise. What they found was the Morris and Monahan one, the straight implementation here does a much better job, but still it's not particularly great. And their fix that they've got here does it much better entirely, okay? So in the case where you have zero viscosity, the sound wave will keep going really nicely in SPH, and what they're getting close to is having zero viscosity here, okay, in their box, okay? So that's good. So I would say at the moment that's probably the state of the art. And one of the things they've kind of shown with that is that if you have a Keplerian ring, they even put this thing called the balsara switch on, which Tom mentioned in his lecture. You have a Keplerian ring around some sort of central source here, some central point mass, and you just watch it for several orbital times. You see that just with the standard SPH, you end up with all these weird structures, and that's just because the SPH viscosity then creams energy out of the system. You then get these, you transfer angular momentum, so the gas falls in, it builds up around this, this orbit here, and it forms these structures, which then fragments, and it's all horribly, horribly artificial. And they found that with their fix and the limiters, they can actually get that to behave much, much better. Okay, so then you get actually back to a properly invested SPH. Okay. So that's good. So a brutal test of SPH, and one which I encourage you to try. You've got CERN there, and it's a nice test to do with CERN. You can also do it obviously with Gadget or any other SPH code. It's to set up a shearing box with a sinusoidal velocity curve in x, which is a function of y. Okay, so you've got, if you imagine your box, in the middle of your box, you got the velocity going this way, and along the edges of the box, periodic, it's going the opposite direction. Okay, it's a very simple test, and you'll find that if you sit. So this was Tom Hobble's paper in 2012. He was started off with this nice sinusoidal velocities. This sawtooth thing is what happens after, in SPH after only 4 sound crossing times. Okay, and what's happening is just that the artificial viscosity is bleeding the energy away from the sawtooth, away from the sine, and flattening things out. It's trying to stabilize the shear. Okay, so that's what's happening there. If you reduce the viscosity, it gets better. But what you'll find is that the spread in the particles here gets larger. Okay. And the reason why is that you're not stabilizing the mesh anymore, right? The particles are then able to fly around in different directions. You've only given the velocity in the x direction. It then starts bleeding into the y and z. Okay. So it's a very brutal test. It's a sweet spot somewhere where you get the best possible solution, and you try and beat down the noise. Okay. So if you want to try your new viscosity out, if you've got a new idea of how to put viscosity into SPH, this is the test to do it in. Okay, I encourage you to try it this afternoon. Any questions before I go on? Okay. So much has been made about SPH trying to resolve Kelvin-Helmholtz, and here's a valiant effort by SPH here, right? So it tries to do it, and it goes, oh no, I just can't. Okay, it's like me in the morning getting out of bed, just can't do it, right? So what's going on here? So people have talked about this pressure discontinuity, and they've talked about pressure blip, and it's not entirely obvious to everybody what's going on. So I thought I should actually maybe try and explain actually what the source of this problem is. So when you're setting up the problem, what you do is you have a dense region in the center, which is cold. You have a lower density environment outside, which is hotter. So I've put them in red, and you have the gas here going in one direction, the gas here going in the other direction in the screen, and then you put some perturbation at the interface here, which then excites the Kelvin-Helmholtz. Okay. So that's the initial conditions you use. That's what you think you've got. Okay. So you set up. Remember, SPH gets its density by summing over its neighbors, right? So what it does is what actually comes out of the SPH when as soon as you switch SPH on, it does that. Okay. So it's smoothed that interface. And it's trying to kind of say, no, I don't like having the particles of different densities. This just doesn't work for me. And so it then tries to change them, and you get this intermediary particle here, and these start to lift away, etc. Okay, so that's what goes on. Now the problem is that you've set the entropy of these particles such that these have more, these have less. And so now you've got the problem is that you've totally messed up the entropy of the surface there, and you've changed the pressure. Okay, so if you actually think about what you've done, the pressure you wanted to have is this straight line here, which is what you thought you had in your initial conditions. But what happens is that these particles here are hot and dense, so the pressure actually rises here. These particles here are cold and less dense, so the pressure drops here, and then you have this strange discontinuity in the pressure over the boundary. Okay, so you create a discontinuity in the system, which you would think wasn't there by your initial conditions. SPH sees one by the way it does its sums. Okay, so that's just an intrinsic feature of the SPH. And the problem is then you've got this situation where the two fluids are trying to push themselves apart. They don't want to be close to each other. Okay. All right. So that system can't evolve well. Okay. You've just created something which is entirely wrong. And so the various fixes to it over the years have been. Oh, sorry, went the wrong way. this one. So Dan Price came out with a cure. Dan said, well, you know, any pressure, any discontinuity you have in SPH or any other, you know, any other system which is not doing kind of remosolve or something, you have to smear it out in some way. You have to get rid of that discontinuity. And he said, well, you know, you have to treat it just the same way as you would treating the discontinuities you have in shocks. We're used to doing that. You'd be put in artificial viscosity. Therefore, for this particular type of problem where you have that the pressure becomes discontinuous because of your energy estimate over the boundary, then you should also put in artificial conductivity term. And so he was saying, well, if you just put an artificial conductivity term in where, you know, this is any quantity here, let's say this is energy and energy here, then you just want to say, well, I'm going to flux the energy between the two states, and so it washes out the fact that you have dense hot things and cold less dense things, and you just transfer the energy between those 2 points, and you get a smooth, continuous thing. And when SPH has that smooth boundary, suddenly it's totally happy. It can actually see what it wants to do, and the Kelvin-Helmholtz starts again. Okay. I should say these are the rolls after the second roll. Okay, so the first roll would be over here, then the first roll gets smeared out, and then the second roll grows. That's why I get this large roll here. Okay. And so it's a fix, right? So it's a fix which tries to cure what SPH is screwed up in the first place. And it's the spirit of it is very good because it's in the same spirit as the artificial viscosity. You know, it's something we're kind of used to seeing in SPH codes. And so it's something that we should have been including. The problem is that it's very difficult to work out what the signal velocity should be. Okay, so in this case, you've got the two pressures here, and so it will try and flux stuff across the boundary between the two different fluids n times the pressure gradient. Now, if you've got a collapsing cloud and you're trying to do the heating and cooling in it, you're going to have a pressure gradient just from the fact you've got a density gradient that's produced by gravity. So obviously, this is going to go horribly, horribly wrong as soon as you have a collapsing cloud. Right? So the trick was then, so how do you, the problem with this type of fix is how do you find a good way of switching it off when you really don't want it? Okay, one thing you could try and do is then just put more pressures in here. You could try and calculate the gravitational pressure and say, okay, you know, work out what's there. You should probably also then put pressures you get from the ram pressure, etc. So then you have to make it more and more complicated, and no one's really tried that, and it's not clear that it works in that machine. However, for certain problems, it also, you know, it might work. You know, if you have a large system where you're probably not resolving the turbulence internally, then you could say, well, what's probably fluxing entropy between the two systems is not, you know, conductivity in a sense, it's turbulent diffusion of some sort of sense, which I can't resolve. And that's what James Wadsley was doing in his paper, I think also 2009. Sorry, I missed the date there. 2008 or 2009. If people want to know, they can ask me. And he was kind of having basically the same idea, but he was using subgrid scale for the turbulence, so it's a turbulent diffusion term. And he was doing it in the context of galaxy formation, and was finding he was getting much, much better estimates of the mixing of the two layers, and he's getting closer to the grid codes when he included it. Okay, so that's a kind of a physical prescription for what this thing is trying to do. Okay, so that's kind of good. So that's a cure. There's also perhaps more prophylactic measure is that you could say, well, maybe SPH, the way it's doing its sums, isn't really that good, and we should be thinking about doing something else. Okay, so it's kind of controversial because people are quite happy with the fact that SPH does its sums this way. It has a lot of nice properties. And the problem is you try and start fiddling with those, you then break some of the other properties of SPH. One of the ones that came up, Ritchie and Thomas, again, I'm sorry, I've forgotten the date. Yeah, 2001 or 2002, I think it's. Sorry, I'll find that out for you if you want. And what they decided to do instead was the normal momentum equation SPH has a pressure here and it has a rho squared in the bottom. Okay, and the rho that you've estimated from just doing the sum around the particle masses and taking the smoothing curve into account. And so what they said was, well, you know, that's very sensitive on density. If you rework it like with just the internal energy, specific internal energy, and then put the density to the single power at the bottom, then you still get the same prefactor. This is still the gradient of the this is still the grad P term, the gradient of the pressure, but it's not quite so sensitive to the density anymore. Okay, it's more sensitive to how I set the initial problem up, and if you have heating and cooling, this thing is changing. Okay, so that's kind of good. The other problem is that they then changed the definition of what this rho is anymore. It's not just having this mu times m, the mass of the particle, and the sum over its smooth values from the other particles. Is that you've now got these u's in here. Okay, so again, you've introduced an extra term into the density summation. So you know that is fiddling with the SPH properties a little bit. However, they do find that's pretty good. Okay, so you can get rid of the problems associated with the contact discontinuity in the pressure, basically because now it doesn't see it. Okay, it doesn't create that same problem. It's not creating that weird jump in the pressure anymore. And so when it sees the initial conditions that you've put in there, which was that very specific thing that you normally use for grid code, it actually sees more like what the grid code would see. Okay, so it doesn't have that surface tension term. And I should say that these papers here, so Phil Hopkins and a paper by, I don't know how to pronounce this, sorry, Sato, maybe, and Makino, they've actually, over the years I've done, you can actually have more, you can have a whole family of things which you stick in here, okay? And depending on the problem, then you can choose slightly different things. They've also done this in the conservative form. This one isn't exactly conservative. It doesn't have the SPH Lagrange multipliers in front, which take into consideration the fact that you're changing the smoothing length all the time, okay? So you can put those terms in as well, and they're done in Phil Hopkins' paper and this other paper, okay? So if you want to have a bit more look at that, then go and see those papers at the bottom. And so here's Phil's attempt to do Kelvin-Helmholtz. So the first one was also his, I should say, the first blue movie. This is his second movie now. This is with the fix. You see it actually works pretty well. Okay, so you get the first roll coming, seems to be fine, and the second roll coming. And that was the one I was showing you earlier on that just fell straight back down again. Okay, so with that fix of just changing the way you're doing the SPH summations, you can get the you can make that pressure blip across the boundary go away. Okay. Any more questions? Okay, so some people come up with a while back. So Tom Hobble came up with this point a while back. He said, well, is this actually a fair test of SPH? Is it fair for SPH to have these initial conditions which just have a kind of a sharp jump across the boundaries of the two flows? And what people have pointed out as well is that, I think actually Jim was mentioning this the other day as well, it's often better to smooth the interface between those two things, because even the grid codes, you're going to excite noise along the boundary which isn't there, which you've not put in terms of your perturbation. Okay, so then even the grid codes, you're seeding those rolls with extra grid noise, and you can get a much more, you can get a solution which you can numerically converge to much better if you then smooth the boundary. And so Colin McNally and his collaborators here proposed a smooth initial conditions for this problem. And so you can say, well, perhaps the Kelvin-Helmholtz is just the fact that the whole problem is irrelevant. SPH wouldn't do that anyway. It would always try and smooth that interface between the two boundaries. But that's actually not true, right? So if you have any cooling and heating in your system, you are going to create those problems. And unless you have something like the conductivity, again, Jim was talking about this, I think, on Monday, you are going to kind of create a situation which the SPH can't get into. Okay, so you do need to deal with this. It's not just the fact that the Kelvin-Helmholtz test is unfair for SPH. Okay, it should be able to deal with that. So Tom Hobble came up with a fix a couple of years ago, and he was actually in sabbatical in Heidelberg, and I kind of heard his daily ramblings on this topic, and he was coming up with this idea. He said, well, Paul, these particles, they just keep punching each other. They keep punching each other, and then if there's nothing at the other side to punch back exactly, it's obviously all going to go wrong because the particle is going to wander around. It's like, well, yeah, that's right, but that's what if you derive SPH from the Lagrangian, that's what you expect to have. And in some sense, that kind of makes the system behave in a kind of a stable way. And so what he thought was, well, we should just get rid of that. We should just say, we'll just make the momentum equation dependent on the relative pressure between the two particles. And so particles which don't have different pressures from each other just won't interact. Okay, so that Kelvin-Helmholtz problem, it won't see any problems, right? Well, in fact, actually in this formalism, it might do because you still get density at the bottom, but it's better. Okay. So just don't use it, right? So it's horribly, horribly unstable, and it does a number of really nasty things. If you try putting it in with self-gravity and things, it goes horribly wrong because, again, you've got an extra pressure coming from the gravitational terms. There's also pressure coming from the ram pressure and stuff. So the whole thing just goes horribly wrong. So, I would caution you, please don't use it. If he's here next week, please buy him a drink on my behalf. Apologies to Tom. Say hi on YouTube, but yeah, don't use it. So a similar problem, which is, people keep companies, they come up with this test and say Blob Test. Blob Test doesn't work. SPH is fundamentally different from grid codes. The Blob Test is the same problem as the Kelvin-Helmholtz, exactly the same. It's the same thing that's going wrong. You've got a dense blob, which is trying to be at a different density, but same pressure as its surroundings, and then it just pushed through it. And the whole thing just goes chaotically wrong because it can't excite the Kelvin-Helmholtz instabilities along the boundary, and so it doesn't disrupt the blob in the center. And the basic, so Oscar Egert's come up with this paper in 2007 where he compared various grid codes, and they all did pretty well. They don't, I wouldn't say they all converge. They all have slight differences in them here, but it looks pretty good. SPH just looks rubbish. It just looks terrible. So no, don't use SPH was the conclusion there. But it's the same problem. It's been around forever, and people. It's the problem. Every time you see a new paper on AstroPH that says SPH can't do something, chances are we've known that for 20 years, and Joe Monaghan's been trying to fix it for that time, and he has had some fix along the way, which people have kind of forgotten because either they didn't understand it or they were too lazy to put it into their code. Okay. So if you put the artificial conductivity into this thing, it works just fine. If you put in the fixes for doing the way SPH does its averaging, for deriving its fluid quantities, again, it does just fine. Sorry, I've got actually a movie of that here. This is a movie I got from Tom Quinn. So, someone in his group, Fabio Governato, has been doing this test problem here, where he's got this is Changa SPH with the conductivity terms in, and I think also with this Ritchie and Thomas fix. Right? They didn't use the more complicated one; they just used the straight Ritchie and Thomas. And then the bottom one is Gadget, straight off-the-shelf Gadget. I know the thing stays together, it creates this weird kind of jellyfish thing around about here, and this one breaks up. And that's a little unfair because old Changa would also do this as well if it didn't include those fixes. It's not like Changa's better, right? It's just that they've actually implemented those fixes, and whereas they've taken Gadget and used the off-the-shelf version. So I think that was a little unfair there between these two. Okay, but again, you can see it just works pretty nicely. Okay, so you can get the same behavior as the grid codes in some senses. The thing does break up. It does similar timescales to what people were seeing with with Flash and ENSO and Ramses. Okay.
Why the shock velocity is different in each case?
What, sorry?
The shock velocity. Why is it different?
I don't know. Actually, it's good. This one moves faster, right? That's right. I mean, you're changing the boundary here, right? So it's bouncing off a different thing. I don't know if it's just that. I don't know.
Because the bottom cloud holds together better.
Yeah, you're changing the shape.
Whereas the top cloud mixes a lot, slows down rapidly.
So you're losing the energy from the top system by breaking it up, whereas in the bottom one you're not. Yeah. Yeah. Good question. Yeah, I hadn't noticed that actually looking at the movie. So another test, which is hilarious, is by putting a square into SPH and watching it for a while, and eventually you see after a few times, oh, circle. It just completely gives up and says, I don't like these square things. I want to be round. so it's just like SPH is predicting what would happen if you put in gravity without you having to put in gravity, right? It's trying to be clever and do this problem for you, right? Obviously terrible. And it doesn't matter if you use, so in the top one they're using equal mass particles and then just changing the lattice distribution to get different densities, or if you use equal separations then change the particle masses. Doesn't seem to matter. It's terrible in both cases. And again, that's just that same problem. It's just that surface tension. They call it surface tension here because now you have that contact. So you have that pressure discontinuity happening all the way around the object. So you first pinch out the corners, then you send a wave through the thing, and then bounces again, and then it pushes out the other part. So you get the pinch, you get a wave, it pushes, and eventually becomes a circle. Okay. Terrible. So you can get rid of it, again, just using that Ritchie and Thomas fix or something similar to it. If you put it in, it gets much better. You still see that actually, it's actually difficult to see because of the way the contrast. Actually now even the equal separations but using different particle masses behaves pretty well, and that's actually quite rare in SPH. Normally in SPH, if you used particles of different masses, they behave terribly with each other, pretty much normally because you have some big guy smacking a smaller one, and then the smaller ones then try to work their way through the lattice of the other one. Okay, right? So it doesn't generally work very well. In this case, it actually seems to work slightly better. So that's kind of encouraging. If you wanted to do something like particle splitting and use different types of masses, this one has been shown actually to be more stable of using different masses. Okay. So my conclusion, I'm going to stop probably kind of early here, but yeah, a little bit early. My conclusion is that many of the problems that you've heard about of SPH have been looked at over the years, and so every time you see a new paper on SPH and someone says, I found a new problem, it's probably the same problem, it's not new, go away and look carefully at what they've done. Chances are it's the same problem. It's probably associated to some contact discontinuity somewhere. But more importantly is that most people have probably not implemented them in their codes. Okay, I must confess, I'm also biased with that as well. Okay, I'll stop there, take some more questions if anyone has them. Thanks. questions?
One comment.
Oh, sorry.
So I spoke with Tom Abel about this a little bit when he was here, and he said that he didn't prefer this diffusion approach. I think they actually use like a force averaging approach at the boundary.
Tom Hobble?
Yes.
Well, I mean, where's it going? I've missed Tom's thing now. I mean, his fix essentially is a kind of a force averaging. I'm not entirely sure. I don't know what fix he was talking about there then. But I mean,
No, Quinn. I'm sorry.
Tom Quinn. Okay. Yes. Sure. Yeah. Tom Quinn is using the Vichy and Thomas fix. So where's my? It's backwards. Sorry. Yes, okay. So Tom Quinn is using this one where they're changing the summations. This is the force averaging thing I think you're talking about here. So they're just using a different formalism for the momentum equation. All right, so normally you would have p of the particle here, and then you'd have rho squared in the bottom. The problem is p has gone horribly wrong, right? Because you've got the wrong density. Density has also gone horribly wrong because you've averaged over your neighbors, and so the momentum equation is just screwed, right, at the boundary. Right? So by doing it in this way, you're kind of compensating for that. You're kind of getting around that problem by saying, okay, I just go from internal energy over the effective density, and the effective density has now got the internal energy weighting on it. Okay, so it's more of a pressure-based formalism essentially than the previous one, and the pressure and initial conditions in that problem were constant, if you believe the initial conditions, right? So that's why it does slightly better. Okay. Now again, so Tom would say probably he doesn't like the conductivity term. I think, as Jim was saying the other day, there's certain problems where you have to put some conductivity in term, and otherwise you're just seeded by noise in your system. And so it's good to set a scale for that. So that's what James Wasley is trying to do in his fix here by changing. He's got a different signal velocity that then depends on some unresolved turbulence in the system. Okay. So Dan Price, he mentions this and mentions that you can do it. He also notes that this will give you problems. Okay, he's not saying that's a universal fix. He was just saying this is how you could fix it. The question is then how you would choose that signal velocity. Okay, so Tom's idea of just choosing. So Tom Quinn's actually. I think in Chandra they're doing both these things actually. I don't think they're doing one or t'other. Because James Wasley has this subgrid turbulence thing. Although maybe in that case for the straight test problem, you're assuming there's no subgrid turbulence, so he probably maybe does set that signal velocity to 0. Maybe that's what's happening there. So for that particular test problem, that's maybe the case.
James' motivation was not really this problem.
No, it was galaxy formation.
James's subgrid. What James was interested in doing was doing like metal diffusion in the halos of galaxies, right? So he needed to introduce a subgrid turbulent mixing so that chemicals could be mixed in SPH, right? So that if you blow iron out of a galaxy, the iron could actually get distributed into the IGN. And so that's what, so his subgrid fix was intended as much for the chemistry as it was for the entropy.
In principle, yeah. But then he also noticed that it does fix these other problems just by applying it to the entropy as well. Then you do fix the problem of the two entropy states not mixing.
Right, but if you don't have that sort of part of that subgrid mixing and conductivity term, you might fix this problem, but you still couldn't do metal diffusion properly.
Yeah.
Which is the problem.
Right.
James was trying to do.
Yes?
So I understand that a lot of the old classic problems now have these fixes, and so SPH does work fine, but I'm wondering...
I think that's I wouldn't say it works fine. I think it works better than a lot of people would say it didn't.
Is there any initial setup or application in which I would inherently prefer an SPH formalism to a grid-based formalism?
Well, so people have, some people have said at this meeting that they've been looking at disks forming, for example, in galaxy cluster simulations, and those disks tend to be aligned with the grid axis. Okay, that's probably because they're not using some unsplit scheme for their hydro. I mean, Jim can maybe say more about that, and they may not be using that conservative scheme he's also talking about for the gravity. So that might just be the two effects there. So in that case, SPH will give you a better distribution of the angular momentum. Doesn't care about the direction. Okay, so that is better in that sense. There's also a question, if you had, say, for example, imagine you're trying to do two colliding, if you're trying to model a binary system and you're actually trying to model the stars, the accretion onto a cataclysmic variable or something. The SPH will probably do a better job of doing the oscillations and various things that happen as those two stars move throughout the volume. It doesn't care about the fact the fact that it's trying to move through a grid. I mean, the reason why it was used a lot of time for doing star cluster formation was basically because that was what was available at the time. So a lot of it was just inertia by the community, not wanting to learn a new system. And until more recently, it was also faster for these problems. I think now, the AMR is, it scales much better. It tends to scale much better than the SPH codes do. So, so you could argue that now the AMR is is a better way to go. And also, then you can also put in things like the MHD much better. Okay. Mark's going to say.
No, I can think of one problem that I tried to do with the AMR. It's horrible. You shouldn't do it. And it has to be fine. That is a black hole falling onto the galactic center, getting sheared apart and forming a disk before it starts the disk. And the reason that's hard to do with any grid-based code is that the sound speed in the cloud is tenths of a kilometer per second, and it's getting sheared and as it falls around the black hole at hundreds of kilometers a second. So it's trying to affect at Mach 1,000. And no grid makes sense. You can if you sort of beat on it enough, make it sort of work. But affecting things at Mach 1,000 across a grid is almost always bad.
Well,
You disagree?
yeah, unfortunately you missed Tuesday morning. Yeah, I mean, I guess the problem with the grid is the time step would be really small if you're doing it Mach 1,000.
Well, and also,
Nothing
then
inherently wrong.
you need a dual energy formalism, right? Otherwise, the internal energy is smaller than the truncation energy compared to the total energy.
Yeah, there's an issue with total energy formulation, but you can do a dual energy formulation. That's not, it's not the underlying grid that's the issue. It's whether you're using a total or internal. So Zeus uses internal energy. You use Zeus. Zeus is a big code. It'll get back to Mach 1,000, and so it's not so much the grid code per se that's the issue, but perhaps energy creation. I mean, I think that is a challenging problem. Possible to do.
More questions? Okay, I think we have a half-an-hour coffee break. Thanks.